Hey everyone, and welcome to my channel. Today we're going to be taking a deep dive into the world of calculus. Specifically, we're going to be learning about the derivative of the tangent function. Now, I know what you're thinking, calculus can be pretty intimidating. But trust me, with a little bit of explanation and some cool visuals, we can break it down into something that's actually pretty easy to understand. So, let's imagine we have a circle with a radius of 1 unit. Now, draw a line from the center of the circle to a point on the circle. This line forms an angle of x radians with the horizontal axis. We can also see that the length of the vertical part of the line is sine x, and the length of the horizontal part is cosine x. Now, let's increase the angle by a tiny amount, dx. What happens to the vertical and horizontal parts of the line? Well, the vertical part will increase by cosine x times dx, and the horizontal part will decrease by sine x times dx. This is because as the angle gets bigger, the vertical part gets longer and the horizontal part gets shorter. To know why that is the case, you can refer to the video links given in the description. But what about the tangent function? The tangent function is simply the ratio of the vertical part of the line to the horizontal part. So, tangent x equals sine x divided by cosine x. Now, we can see how the change in angle, dx, affects the tangent function. To understand this better, let's express the tangent function in terms of sine and cosine components. We can also represent the tangent function at angle x plus dx in the same way. The difference between these two expressions will give us the change in the tangent function for a small change in angle, dx. Before we continue, let's simplify the equation a bit. This will make it easier to see what's going on. We can do this by isolating the changes in terms of sine and cosine. This will also give us a better geometric understanding of what the change in the tangent function looks like. The tangent function tells us how many cosine components can fit into the sine component. So, for angle x plus dx, the sine component increases and the cosine component decreases compared to when the angle was x. But to see exactly how much it changes is a bit tricky. This is because the change in length happens in both the numerator and the denominator of the tangent function. To see the geometrical meaning more clearly, we can split the numerator of the equation. The first term represents the change in the tangent function due to the change in only the denominator value, which is the change in the cosine function. The second term represents the change due to the change in the sine function. The first term reflects the change in the tangent function due to a change in the denominator, cosine function alone. Red signifies filled space, while blue represents empty space. If we fill the sine side with the same number of resized cosine sides as when the angle was x, we get the number to be equal to sine x divided by cosine x. However, there's still some uncovered length on the sine side. For each red part, there's a corresponding blue part, totaling tangent x blue parts, each with a length of sine x times dx. This gives a total uncovered length as tangent x times sine x times dx. Using cosine x minus sine x times dx as the denominator introduces second-order terms in dx, which are negligible for small changes. So, we approximate the denominator as cosine x, resulting in a change in the tangent function due to the first term of tan squared x alongside the original tangent x value. In the second term, we observe first-order changes in both the numerator and denominator, leading to second-order changes dx squared, which we want to avoid. By neglecting the minus sine x times dx term, we get a simplified value of 1 dx. Combining the simplified terms, we obtain tan x plus dx, with the isolated changes as tan x plus tan squared x times dx plus 1 dx. Removing the original tan x value leaves us with only the change, d tan x, which simplifies to secant squared x times dx. Finally, taking the ratio of the functional change, d tan x, to the angular change, dx, gives the derivative of secant squared x. Now, let's explore the derivative of the tan inverse function. This function performs the opposite of the tan function, taking a tan value x as input and returning the corresponding angle theta. We can derive the tan inverse function's derivative using the derivative of the tan function. Here's the process. The first step is to replace x with theta. Since the angle isn't the independent variable here, we follow notational conventions and use theta to represent angle. This allows us to express the derivative of tan in terms of theta. The second step is to treat tangent, theta, as the independent variable x. We substitute all terms with x because we need the equation in terms of the independent variable. The third step is to take the reciprocal of the equation. This gives us the ratio of the angular change to the change in the tan function. By following these steps, we obtain the derivative of the tan inverse function. And there we have it. We've journeyed through the fascinating derivatives of the tangent and its inverse, hopefully making these concepts a bit more clear. If you enjoyed this exploration, please leave a like and subscribe for more intriguing math and physics content. Don't forget to share this video with others who crave learning adventures. Happy exploring, and until next time.